Imagine a cosmic flash so powerful that it can wipe out life on Earth, not with fire, not with earthquakes, not with a plague, but with light itself. Gamma-ray bursts, or GRBs, are the universe's most energetic explosions, releasing in seconds more energy than our sun will emit in its entire 10 billion-year life. Scientists have detected them billions of light years away, yet their influence could extend far closer. Could such a phenomenon strike Earth? Could a distant star collapsing into a black hole, or two neutron stars colliding, actually end all life here? The story begins in the 1960s, when satellites designed to monitor nuclear tests unexpectedly detected bursts of high-energy gamma radiation from space. No known astronomical event matched the intensity of these flashes. Over decades, GRBs became recognized as the universe's ultimate cosmic lighthouses, terrifying and untouchable, yet telling a story about the power and danger that exists beyond our solar system. Long GRBs, lasting more than 2 seconds, are linked to the death of massive stars, stars far heavier than our sun, collapsing into black holes. Short GRBs, lasting milliseconds to seconds, occur when two neutron stars merge, a violent ballet producing energy capable of outshining an entire galaxy. And while the beams of gamma radiation are focused, precise, and narrow, the thought that Earth could fall directly in one enough to capture the imagination and fear of scientists and the public alike. But understanding these bursts is not just about panic, it is about perspective. GRBs illuminate the universe's extremes, the fragility of planetary life, and the delicate conditions required for survival. They offer a window into the cosmos' most violent processes and allow us to evaluate our place in a universe where energy can destroy worlds in moments. As we journey through this story, we will explore how GRBs work, why they are rare but dangerous, and what evidence suggests they may have shaped Earth's history, including possible links to mass extinction events. We will examine the physics, the probabilities, and the consequences, painting a picture both terrifying and scientifically grounded. This is not science fiction. It is the reality of the universe, and it may very well have brushed against our planet before, shaping life in ways we are only beginning to understand. Gamma-ray bursts are not random flashes scattered across the sky. They have identifiable origins and a consistent logic. Long GRBs occur when massive stars, often tens of times the mass of our sun, reach the end of their life cycles. Their cores collapse into black holes, and in the process, jets of gamma radiation shoot outward at nearly the speed of light. These jets pierce the surrounding stellar material, and if aligned with Earth, their impact could be catastrophic. Short GRBs, though briefer, are equally violent. When neutron stars, remnants of previous supernovae, spiral into each other, their merger produces intense gamma radiation, gravitational waves, and sometimes heavy elements like gold and platinum. These collisions are rare but incredibly energetic, often detected across billions of light years. The danger comes not from visible heat or shockwaves, but from the ionizing power of gamma rays themselves, striking Earth's upper atmosphere. Gamma radiation splits nitrogen and oxygen molecules, creating nitrogen oxides. These chemicals catalyze the destruction of the ozone layer, allowing lethal ultraviolet radiation to reach the surface. Life on land and in shallow oceans would be exposed to deadly UV, while deeper water ecosystems might remain shielded. Yet Earth is relatively safe compared to the vast universe. Most GRBs occur in distant galaxies or far from the Milky Way's habitable zones. Even if a GRB occurs in our galaxy, the beam would need precise alignment to hit Earth. Statistically, such a direct hit might happen once every hundreds of millions of years, making it rare but not impossible. Historical records in geology hint that gamma-ray bursts may have already influenced life on Earth. Some scientists suggest a correlation between GRBs and the Ordovician mass extinction, roughly 440 million years ago, when marine life suffered massive losses. Evidence includes isotopic anomalies in sediments that could be linked to atmospheric changes triggered by intense radiation. Understanding GRBs requires more than fear. It demands perspective. They are both destructive and illuminating. They demonstrate the scale of cosmic energy and the vulnerability of life on a planetary surface, and they provide clues about the conditions necessary for life to persist, not just on Earth, but throughout the galaxy. The question that haunts scientists and the public alike is simple. Could a gamma-ray burst actually wipe out life on Earth? The answer is complex, rooted in probabilities, cosmic distances, and the precise orientation of a burst beam. Unlike asteroids, which strike predictably within our solar system, GRBs originate light years away. Their danger is not in visible impact, but in subtle, invisible destruction. Gamma rays hitting the atmosphere would trigger chemical reactions, primarily breaking apart nitrogen and oxygen molecules. The result? Nitrogen oxides destroy ozone, the shield that protects life from ultraviolet light. In mere seconds, the surface could become exposed to UV levels strong enough to devastate terrestrial ecosystems. Crop failures, mass die-offs of plankton, and collapse of the food chain could follow. Even species adapted to radiation might struggle to survive prolonged exposure. But the conflict extends beyond biology. GRBs challenge our understanding of probability and cosmic luck. Earth resides in a relatively safe part of the Milky Way, a galaxy rich in heavy elements, but lacking in many of the conditions that produce long GRBs. Most dangerous stars are rare, massive, and often found in low metallicity galaxies common in the early universe, and yet, the very fact that a burst could hit Earth means that life exists on a knife's edge, dependent not just on physics, but on cosmic geography and timing. Historical evidence hints that Earth has narrowly escaped catastrophic GRBs in the past. Some researchers link the Ordovician mass extinction to a gamma-ray burst, suggesting that sudden atmospheric changes and UV exposure could have caused widespread species loss. Other extinctions may bear subtler imprints, encoded in isotopes or geological anomalies that hint at cosmic radiation events. These possibilities transform the conflict from abstract to tangible. Life's survival is contingent on events billions of light years away, indifferent to our existence. Furthermore, the nature of GRBs themselves compounds the tension. They are brief, seconds to minutes, but their consequences unfold over years. A single event could trigger a chain reaction: ozone depletion, climate cooling due to nitrogen dioxide, ecological collapse, and the potential extinction of many species. The very brevity of the burst contrasts sharply with its long-term aftermath, creating dramatic tension between instant cause and protracted effect. In essence, gamma-ray bursts confront humanity with a humbling truth. Life is resilient, but it is not invulnerable. The universe contains forces far larger than we can control, forces capable of shaping the trajectory of evolution itself. And while probability favors our survival, the possibility of annihilation is real, a silent, invisible threat lurking in the depths of the cosmos. Despite the terrifying potential of gamma-ray bursts, humanity is not entirely powerless, at least intellectually. The comeback in this story is our ability to understand and predict, to transform fear into knowledge. By studying the universe, astronomers can identify stars likely to produce GRBs, assess their distances, and evaluate the risks for Earth. Modern telescopes like NASA's SWIFT and the Fermi Gamma-Ray Space Telescope continuously monitor the sky for gamma-ray bursts, cataloging every detected event with extremely high precision. Scientists can trace their origins, estimate their energies, and model how such radiation could interact with planetary atmospheres. These observations allow researchers to evaluate the real level of risk. Gamma-ray bursts are rare on cosmic timescales, and even among them a direct alignment with Earth is considered highly unlikely. Understanding the physical mechanisms behind these bursts also highlights Earth's resilience. Atmospheric models suggest that even if a powerful burst were to affect the planet, the damage would not necessarily be permanent. Nitrogen oxides produced in the atmosphere gradually break down over time, and the ozone layer can slowly rebuild, restoring its protective role over decades. Many forms of life have endured extreme environmental stress in Earth's past: microorganisms, deep-sea organisms, and resilient ecosystems shielded by water or rock could survive even severe radiation events, allowing life as a whole to persist. Beyond the physical effects, there is a broader philosophical perspective. Gamma-ray bursts reveal the delicate interplay between chance and survival. Earth's location in the Milky Way, the relative scarcity of dangerous progenitor stars nearby, and the orientation of cosmic jets have all contributed to long-term stability. This does not mean humanity is invulnerable, but it does show that survival is shaped by physics, probability, and cosmic geography rather than intent or hostility. This understanding transforms fear into respect. Instead of focusing on apocalyptic scenarios, humanity can channel curiosity, scientific rigor, and long-term thinking. Recognizing the fragility of life highlights the importance of planetary protection and continuous monitoring of cosmic threats. Agency is reclaimed not by altering the universe, but by understanding it. Gamma-ray bursts, once viewed only as symbols of destruction, become tools for scientific insight. They demonstrate that life exists in a dynamic and sometimes hostile universe, and that knowledge, observation, and reason are the most effective shields available to us. While we cannot prevent such bursts, we can reduce uncertainty, study their effects, and prepare future generations to understand the cosmic environment in which civilization exists. As exploration continues, the story expands beyond Earth. Gamma-ray bursts are not only local threats, but cosmic forces capable of influencing entire galaxies. They illuminate the energetic extremes of the universe and help define where life can safely exist. Planets located near dense star clusters or close to galactic centers where massive stars are more common likely face a higher probability of exposure to intense radiation. This cosmic geography suggests that the distribution of life in the universe may be constrained by such events, potentially making long-term habitable regions rarer than once assumed. Studies of exoplanetary systems indicate that stars similar to our Sun are often found in relatively calm regions of their galaxies, far from areas prone to frequent gamma-ray bursts. This supports the idea that Earth resides in a galactic safe zone, a quiet region where life has had the opportunity to evolve over billions of years without repeated sterilizing events. Understanding these patterns helps refine the search for life beyond our solar system by focusing on regions with lower exposure to extreme cosmic radiation. The narrative becomes darker when considering the impact of a nearby burst on a technologically advanced civilization. Unlike primitive life, which might survive deep underground or beneath oceans, intelligent life relies on complex technology and infrastructure. A sudden influx of gamma radiation could disrupt satellites, communication networks, and power systems, reminding us that even advanced societies have limits when faced with rock cosmic forces. The immense scale of these events also invites philosophical reflection. Gamma-ray bursts are indifferent to life. They do not target, punish, or choose. They are natural consequences of physics operating at extreme conditions. Survival therefore depends as much on luck and location as on intelligence or technology. Life on Earth has already endured mass extinctions, asteroid impacts, and ice ages. Gamma-ray bursts represent another factor in the vast and different theater of the cosmos. Yet this tension also fuels curiosity and wonder. By studying these events, humanity gains deeper insight into star formation, black holes, neutron star collisions, and the evolution of the universe itself. Each detected burst adds another piece to the puzzle of how matter, energy, and life are interconnected, transforming fear into understanding and preparing humanity mentally and scientifically for a universe shaped by forces far beyond direct control. In this phase of the story, gamma-ray bursts act simultaneously as both villain and teacher. They expose the precariousness of life while offering humanity a deeper understanding of the fundamental processes that govern the universe. As the journey into the nature of gamma-ray bursts comes to a close, the true payoff is not limited to recognizing their destructive potential, but lies in understanding their broader role in the cosmic order. These events remind us that the universe operates on scales of energy and time far beyond human intuition. Gamma-ray bursts are not malevolent forces acting with intent. They are natural outcomes of stellar evolution, the final moments of massive stars collapsing and neutron stars merging. In this sense, they are inseparable from creation itself, as the same processes that generate destruction also produce heavy elements that form planets and make life possible. The threat they pose is real but exceedingly rare. For a burst to cause catastrophic effects on Earth, it would require an unlikely combination of proximity and precise alignment, making such an event improbable on human time scales. Yet rarity does not diminish significance. By studying gamma-ray bursts, scientists gain insight into the life cycles of massive stars, the behavior of black holes, and the origin of the elements that compose worlds and living organisms. Every detected burst serves as a window into the forces that shaped the universe long before Earth existed. This understanding also reframes humanity's perception of resilience. Life on Earth has endured asteroid impacts, intense solar activity, and dramatic climate shifts. The possibility of a gamma-ray burst adds another layer to this long narrative of survival, emphasizing the fragile balance that allows habitability to persist and underscoring the importance of planetary conditions that remain stable over immense spans of time. Earth's position in a relatively calm region of the Milky Way may not be accidental. It is a quiet corner where life was allowed to flourish, evolve, and eventually reach a stage where it could observe and interpret the cosmos itself. Gamma-ray bursts also compel philosophical reflection. They challenge assumptions of safety and permanence and confront the idea of the universe as a benign environment. They reveal that persistence depends not on dominance or control, but on a combination of location, probability, and resilience. This realization does not lead to despair, but instead encourages humility, caution, and deeper curiosity about humanity's place in the cosmic landscape. Ultimately, the story of gamma-ray bursts reflects the universe's dual nature, overwhelming in power yet rich in lessons. These events encourage exploration, observation, and preparation grounded in understanding rather than fear. Each burst recorded and each model refined brings humanity closer to grasping the immense scale of cosmic processes and the fragile beauty of life on Earth. While a gamma-ray burst could in theory threaten life itself, it also strengthens awareness and perspective, transforming the narrative from helplessness into comprehension. Through the study of these cosmic explosions, humanity learns not only about destruction, but about endurance, adaptation, and the remarkable capacity of life to persist in a universe shaped by both danger and wonder. In the faint, silent light of distant gamma rays, we glimpse both the vulnerability and the potential of our world, a perspective that is humbling, inspiring, and profoundly human.